Good afternoon, everyone. Welcome to track 4 at 1300 hours. Sorry? You can't hear anything. Okay, now you can. All right, track 4, 1300 hours. Welcome, everybody. This promises to be a riveting session. So, okay, how's this? I would ask that at the end of the presentation that you don't come up to the front of the stage. I believe we're going to Capri 114 for Q&A. This is Jonathan Lee and Neil Pahl. Go ahead, guys.
Thanks. Hey, everyone. Thanks for coming. So we're going to be talking about smart card authentication and blocking debiting on stored value systems. Louder? This good? Raise the mic. All right.
First off, I want to say that it's just a pleasure to be in front of everyone. It's our first time at DEF CON, so be a little bit easy on us.
Yeah, it's been pretty awesome so far. All right, okay. All right, so let's get started. So who are we? I'm Jonathan Lee. I'm a computer engineering student at UBC in Vancouver. My interests are electronics and embedded systems.
I'm Neil. I'm also a UBC graduate out of Vancouver, but I'm from an electrical engineering background. Recent graduate and looking for work, if anyone could do anything about that. So just first off, before just to set off your expectations here, we're going to have a quick disclaimer. We're not exactly security professionals. We're university students and graduates, so I'm not lead code-breaking hackers here. We didn't exactly break any encryption schemes or crack those, but we'll show that with our limited security knowledge, we were able to compromise what was thought to be a secure system. So what do we know about security? We just took a brief intro to computer security class, just some basic fundamentals with some basic cryptography, authentication protocols, and all that. Just a bit of that stuff. So our motivation for this project, basically for our class we had to do a term project, which was a security analysis on some sort of secure system. We thought it just an opportunity to try out some cool hacks. I know John was a resident at UBC, so he had a good eye on, it was beneficial to him to get access to this system.
Thanks, yeah.
So why should you care about our hack? Well, we all know, anyone out there who's security professionals know that companies spend a lot of money and time to secure their systems. And basically, for this system, it has a lot of security features that they advertise. And basically, if you're able to get around those, then they don't mean much, and it's a lot of waste of time.
So just a bit of history on some of the smart card hacks that have been done previously. Actually, these two presentations were done at DEF CON before, and they really emphasize the need for authentication and encryption on these communications and these transactions. Joe Grand did an analysis on the San Francisco parking meter system, and Strom Carlson did an analysis on the FedEx Kinko card. Both of them were vulnerable to replay attacks, so if they were just able to record, especially with the FedEx card, if they're just able to record the password, they could get into the card and do whatever they want, write a new value. It was pretty insecure. So they really emphasize the need for authentication on the communications. So this is the target system, just a smart card laundry system, a stored value system. That's what's important here. It could be anything really, but the one that we had access to was a laundry system. So some of the early efforts, we were thinking of just trying some of the usual attacks. We didn't really know which chip was on the card yet. We didn't know anything about it really. We were thinking, could we just simply read and modify the contents of the card without anything, or do we have to sniff some read-or-write passwords, or could we perform any replay attacks? So yeah, we started off thinking about those, and in our early investigations, we did some Google searches and we found a blog of someone who actually looked at the same system, and his success was limited to just reading the configuration memory off of the card, and we'll tell you what that is in a second. And we also weren't sure if that was a card that we had either. We just assumed that it was the same one. So we were later able to identify the card as Atmel CryptoMemory based on the ATR that you see here. There's a block diagram here of what the chip looks like underneath. Probably something to note is the authentication and encryption engine that you see in the top middle block. Some of the security features of this chip, after looking at the data sheet, we've noticed that it had 64-bit mutual authentication protocol, encrypted checksums on every message containing data, and encrypted those checksums using stream encryption, and it had a bunch of other stuff that wasn't really relevant to this talk.
So on top of those things, when we looked through the datasheet, we found out that it does run under. It has 3 capable security modes which it runs under: standard, password mode, and also authentication mode. And then it can enter in encryption mode as well. So the default mode is just a standard password mode, where any configuration data, user data, and passwords are all sent in the clear. And then on top of that, if it wanted to enter authentication and encryption modes, it had to perform the authentication sequences and the proper commands for that.
So we decided to take a look at how our card was configured. Since the configuration memory is sent in the clear, we don't need any special permissions to read it. And I should also make the distinction between configuration memory and user zone memory. Configuration memory just tells us how the card's configured, whereas the user zone memory is separate and contains like the values, history, things like that. So I just got a simple USB smart card reader off of eBay, and then using the smart card IO Java library, I just quickly wrote something to dump the configuration memory.
Yeah, at this point we didn't actually confirm it as well, so another try we would have just tried to read from the user zones and then try to rewrite new values. His program allowed us to dump the configuration memory here. So just taking a look at it, and we're going to interpret this. In the first row, it just says the addresses where the configuration memory starts. And then at the end, it shows the status of our read command. So 9000 just says that memory is accessible. And then 6900 just shows that memory we didn't have any access to. Just taking a look at some important memory values there. The data configuration register, the bitwise value of it is just shown there. And what we learned from that is that only 4 authentication attempts are allowed on this card. Authentication attempts counter was enabled, so we do have to worry about that. Other important registers are just the access registers. The bitwise data shows to be there, and what we learned from that is that encryption isn't necessarily necessary for this card or system, and then also it's not using any read or write passwords. But what we did find out was that the authentication mode is required to read from the user zones. So just summing that up, what we learned here is that we weren't able to do any kind of brute force key cracking because the counter is enabled. Also, because there's no encryption, we thought maybe we would be able to sniff some passwords, but it turns out they're not even using passwords, so we won't even be able to sniff them. And then finally, we found out the most daunting information was that it actually requires an authentication. So if we recall the security modes, it's in the authentication mode. That shows that user data is shown in the clear as it's transmitted, but then the passwords are encrypted, which we don't need again. And what's most important is that after it sends data, it uses a MAC value to check the integrity of the data and make sure that it came from the proper source. So we learned from that basically that ruled out any replay attacks because every session will be different than the previous.
So yeah, so that kind of sums up our early findings, and we kind of hit a brick wall here. We weren't really sure what to do. There were 6 weeks left in our project, and we didn't have the time or the expertise really to do a proper crypto analysis of the authentication protocol. So we were kind of took a step back and thought about our approach. The whole time we were thinking about how can we modify the contents of the card? How can we hack the card? But really we didn't think about the entire system working together. So we started thinking about, okay, well, what about the machine? Our goal here is to just get free laundry. So screw the card. What about the machine? Is there any vulnerabilities there? And then maybe the communications between the card and the machine. So we try to come up with a logical hypothesis of the state machine of the laundry machine and how the communication flows. So if I were a lazy programmer, this might be one way to do it. Simply on the host side, so the machine side, just initiate the authentication procedure, and after that's finished and each side is verified, just read the value off of the card, wait for the user to hit the start button, and then write the new data onto the card, the lesser data, which means that you just debited the card. We thought this was a bit of a long shot, that they actually implemented it like this, but we decided to take a look. So, if it were implemented like this, there might be an opportunity for a man-in-the-middle attack right here. So just, if you don't know what a man-in-the-middle attack is, it's just having an entity in between two parties that want to communicate, and this entity can intercept communications going both ways and possibly modify the communications for its own purposes. And we were wondering if we could apply this in hardware as well. But before we did anything else, we actually had to look at the communications between the machine and the card. So I'll let Neil talk about that.
And this is where things got a little bit interesting. We all had to get a sniffing. We had to start sniffing. And if you can imagine us sitting in the middle of our dorm room holding a laptop connected to all these wires into the laundry machine, it drew a little bit of attention to anyone trying to do their laundry. And
yeah, we got some interesting looks.
We ended up doing a lot
of people just didn't even care either. Like they didn't even look at us. They just went in there and did their laundry and left, and we just were just sitting there sniffing communications.
So the first thing we needed was just a prepared smart card, where other people have tried using a shim and all that kind of stuff, and we thought the easiest way is just some copper tape and then solder to the contacts there would allow us to have access to the pins which we needed. We also were able to purchase a USB logic analyzer. We just found that online, and that was about $200.
Yeah, it was about $200, and that's a SAILI logic, USB logic analyzer. It was really crucial for our project and also debugging our hardware that we'll show you later.
All right. So basically, the communication went under 9600 baud. It was a byte-by-byte data transmission in the form of 8 data bits, even parity, and 1 stop bit. And then to form a command, just a group of bytes will be sent along the line. So let's just take a look at the communication flow. As soon as you put in the card into the machine, the first thing that happens is that the card sends out its answer to reset, where it shows which card it is for the machine. The machine then reads the 8-bit cryptogram and 7-byte
8-byte cryptogram.
8-byte cryptogram and 7-byte ID.
Bits and bytes.
And then it uses this cryptogram to compute a challenge value, which it then sends along with a random number. It's pretty much just the textbook mutual authentication protocol, which it carries out here. And then finally, it reads the new cryptogram from the card, which the card generates from those, to verify that it is the proper card. The machine then proceeds to read from the user zones. After the user presses the start button on the laundry machine, we found out that it reads from the user zones, and then it writes newly decremented value to the card.
Using 3 separate write commands.
Just note here that every read and write command follows with a checksum to verify that the data was only sent by the proper parties.
And that would be the MAC that Neil was talking about earlier, the MAC, message authentication, something like that. Or anyways, but it's an encrypted checksum.
So just taking a closer look at the final write commands, we'll see here on our picture, that comes out, that the first thing that's sent is a five-character command, which shows us the instruction code, the address, where it wants to head and also the number of bytes that it's going to send. The card then replies back with the instruction code, and then the machine proceeds to send the data bytes. After that, the card sends back another reply saying to wait for the checksum. And then the checksum is sent, 5-character command. The card replies again, and then the checksum, and then the card says, okay, it has been written to the spot. So if we recap what happened there, it basically just shows that after the start button, it reads and then it writes. So luckily, the last thing that happens is that it writes to the card, so maybe we have a chance to block that. So if you call that writing process, what we did notice is that the machine always expects the same replies back from the card. So that isn't really secure there.
Yeah, it opens up an opportunity for us to insert those replies
at the proper timing.
Yeah,
and
at the proper timing. So
yeah. So basically, what happens here is that the machine is never fully assured that it performs the right command on the card. What someone would need to do is just fake this reply, block the data bits
from going to the card,
fake the other status, and then on the checksum, just do the same thing, fake the card replies, which are predictable. So if we just take a look at our hardware implementation of it.
Yeah, so this is our man-in-the-middle circuit here. We got a microcontroller. Neil donated his Costco ID card. If someone found this, it wouldn't be too hard to track us down. For our dummy card, and it also has a smart card slot to pass in the messages from the machine to the card. So a high-level diagram of our hardware here. The microcontroller that we used was an Atmel Atmega 164P, and we had a mux switch here. We can just basically think of it as a switch. And in one mode, we would allow. So we had two strategies to forward bytes using this man-in-the-middle. Okay, I'll talk about the microcontroller forwarding first. In the microcontroller forwarding, the mux switch is open, and all communications is passed through the microcontroller. So in one UART of the microcontroller and out the other. And then the other strategy, we just close the switch on the mux, and basically it's just like a wire, or not. Well, yeah, it's basically like a wire between the machine and the real card. So as if nothing were there. So here was what it looks like with the mux switch closed. The top line is going to the laundry machine. The bottom line is going to the card. And as you can see, there's no delay on both sides of the mux switch. It's byte for byte. It's going forward without any delay. And then if we're forwarding through our microcontroller, you can see here that there's a 1 byte delay because we have to read 1 byte, then put it out in the line, read 1 byte, put it out in the line. So you can see going from the machine to the card, you can see it going in one direction, and then going back from the card to the machine, you can see it going forwarding in the other direction. So that's basically what it looks like. So onto the actual exploit. What we did with our microcontroller is we entered our microcontroller forwarding mode, and we just looked for the right commands. And as soon as we found them, we just severed all communications to the card. So the card sees nothing at this point. On the card side, it just looks like the communications just dropped out. But on the host side, the laundry machine, we've inserted some key bytes here to trick it into thinking that the card is still there, and to just keep going with the communications. As you can see, so we inserted the instruction byte that it expects to see, and then the host machine just started spewing out the data. So it thinks that the card is still there, but in reality, none of the communications is going to the card anymore. So that was actually enough to fool the machine into starting, and without ever writing to the card. All the components that we used to build this was less than $15, and if we wanted to, we could probably even make it cheaper. But,
good price for free laundry, I'd say.
Yeah. But we weren't exactly done there. Even though this fulfilled the requirements of our school project, And we got a pretty good mark on that, but we wanted to see what else we could do with this, with this man in the middle here, because we had this nice circuit. We could forward bytes as we please, and also change communications as we please. And we just wanted to see what else we could do. So I'll let Neil talk about some of the hypotheses that we came up with.
So another thing we just tried is just allowing it to reach the authentication state, and then use our man-in-the-middle hardware to just dump the protected user zones. So we see here that we just injected the command afterwards to read from the card, 7F bytes from starting at 0, and then the smart card just told us everything it had to say.
Yeah, so I think just a note here. What we're reading here is the user zone memory. So this is the part that's actually supposed to be protected by the authentication scheme. But because we have a man in the middle, we can just wait until it reaches the authenticated state, and then just choose to insert whatever we want after that. And that's enough for it to start spewing its guts, really.
All right, just take a look at the user memory. We found out that this system uses a history buffer, which is standard practice for stored value cards, so that you can see the previous decrements. It basically has one reference value which holds the location of the value, and then the value is stored into different slots, memory slots. Just to walk through how it would work is it would read from the reference value, and then it would read from the slot, the appropriate slot, the value of the card. It would write the new value onto the next slot, and then it would update the reference. Then it would do it again, fill up the buffer, and then so at this point we have a full buffer. The reference is at the third spot, and we figured, can this system be manipulated? And then a hypothesis that we had was that when the final memory slot is reached, what if we read the reference value, read from the value, so the machine sees enough money on the card here, and when it wants to decrement the value, what if our man in the middle was able to redirect that writing to the same slot back to where it was? If that was able to happen, basically, when you updated the reference to the card, you'd be sitting at the initial value that you started with, $5. There was a reason why this type of attack would be beneficial to the first attack that we started, because if you would have read afterwards, this attack would be available. So if we're possible to redirect the write command, what else would be possible? Could we have changed the values on the card? So we see here, if our man in the middle would have been able to overlap the two slots. Cool graphic. And then, so we look here, what value would the slot 1 hold? So if we were able to figure out what that value was, how the system worked, like how the data would have been stored, and then somehow intelligently pick a good spot to create a new value, then. So we tried that out, and it turns out you're unable to write to different locations.
Yeah, so basically what we found out here was we tried to redirect the write. So the highlighted in yellow here is the address of where you want to write to, and we had swapped that with something else. But further along, when it asked for the checksum, it determined that the checksum was incorrect. And the reason for this is because it uses stream encryption. At first, we weren't sure if the encryption just worked on the data or the entire message.
Yeah, the data sheet said that the stream encryption was affected by data that was transferred, not.
Yeah, so basically.
So we were hoping that maybe it didn't include the command as well.
Yeah, so basically every byte that shows up on the line here will change the state of the cipher stream. And so changing one byte was enough to throw the card's cipher stream out and the host machine's cipher stream out, such that the generated checksum, or the generated encrypted checksum, wouldn't match in the end. So, in summary, wow, we really blew through this. In summary, communications that end in a write command are not secure. Now, you might think, okay, well, the simplest thing to do is just to end in a read command, right? Write your new value, and then immediately follow that up with a read to verify that what you just wrote is there. That seems pretty obvious, but in this Atmel application note, which tells you how to implement a stored value card for, using CryptoMemory for this purpose, they specifically say to do that bad behavior, to write to the card and then power down, like step-by-step instructions of what to do, and it's in their app note. So the reason why we named Atmel in this talk is because we think that maybe a lot of people use this app note to design their systems, and if that's true, then it could be possible that this attack works on a lot of different Atmel CryptoMemory-based stored value systems. And certainly the communications that we sniffed was very close to what they laid out in the app note, almost transaction per transaction. And yeah, and the other vulnerability here is that we were able to dump the user zone memory using the man-in-the-middle after letting the authentication go through. So the fix for this is just to simply use the features on the card. So use the encryption mode, which is the next step up from the authentication mode. So this encrypts everything. This encrypts the data, so we wouldn't be able to read it. And also on the host side, you should introduce some sort of tamper detection circuitry. Our circuit that we tacked on actually used the VCC of the machine, so the 5 volts off of the machine, and we were able to power our entire man-in-the-middle circuit using the power there. And it's easily drawing more current, like orders of magnitude more current than what that little chip on the card would. So it'd be pretty easy to detect if there's something latched on there. So that's one thing to look out for.
Now on to the montage video. So you can see here it's not started yet. And then we're going to plug that in. The initial balance shows to be 310. So the machine's able to start. It shows 250, but
All right, thanks everyone. We really blazed through that. We were kind of nervous and we spoke really fast. So yeah, basically, just to conclude it, the real lesson here is, I guess one, kind of telling a story about how two noobs, like complete security